Have you ever just stopped and wondered what's actually inside your phone? I don't just mean the apps and the photos, I mean the literal physical layers of stuff, the materials, the machines, the logic that make the whole thing possible. Well, today we're going to peel back those layers. We're going on a journey from the raw elements dug out of the ground all the way up to the verge of artificial thought.
So here's our game plan. We're going to start at the very bottom, with the physical stuff that everything is made of. Then we'll see how we shape that stuff with mind-boggling precision. After that, we'll dive into the code that breathes life into it all, and explore how these machines are actually starting to learn. From there, we'll look at how we interact with this new smart world. And finally, we'll ask the really big questions that all this technology forces us to confront.
All right, let's start at the very beginning. Layer 1. Before you can have a circuit, before you have a robot, before you have an algorithm, you need something real, something you can hold. You need materials.
And this quote really hits the nail on the head. You see, you can't just grab any old material for a job. You have to understand how it's built on a molecular level, how you put it together, and what that means for its properties. Is it strong? Does it conduct electricity? It's all connected. And making that first choice, that's the first step in building absolutely anything.
Let's make this super clear with a classic example. You've got steel, the tough, strong, recyclable backbone of our bridges and cars. And then you've got polymers, plastics, which are cheap, light, and unbelievably versatile. So what do you need? Brute strength or something lightweight? Something that lasts forever or something that's cheap to make? Engineers live in this world of trade-offs, and their choices here shape everything around us. But this brings us to the absolute miracle material of our time, the semiconductor. It's not great at conducting electricity, and it's not great at blocking it. It's somewhere in the middle, and that's its superpower. Because we can add tiny, targeted impurities, a process called doping. We can control exactly how it behaves. We can tell it when to let electricity flow and when to stop it. This creates a perfect, microscopic electronic switch with no moving parts. And that switch, that's the transistor. Billions of them are the bedrock of every single microchip. They are the atoms of our entire digital universe.
Okay, so we've got our amazing materials, but they don't just assemble themselves into smartphones, right? The next layer up is all about motion, about shaping and moving things with a level of accuracy that, honestly, no human hand could ever hope to achieve. This is the world of precision mechanics.
And this is where the industrial robot comes in. Just think of it as the ultimate programmable arm. It can twist, turn, and move in any direction, doing things like welding a car frame or placing a tiny chip on a circuit board. And it does it perfectly, the exact same way, 24 hours a day without ever getting tired. These things are the real workhorses of the modern world. But wait a minute, how do you know that robot did its job perfectly? How do you check that the part is flawless? Well, you bring in the ultimate inspector, the coordinate measuring machine. It's incredible. It has this hypersensitive probe that delicately touches an object in thousands of different spots, building a perfect 3D digital map. Then it compares that map to the original design, down to the micrometer, to make sure everything is exactly as it should be.
So you've got this massive, powerful, and kind of intimidating robot. How in the world do you tell it what to do? You don't just sit down with a keyboard and start typing. No, you use one of these, a teach pendant. It's basically a super tough, highly specialized remote control that lets a human operator literally walk the robot through its job, step by step.
And this one device gives the operator total control. They can physically move that giant arm into the perfect position, record that point, link it to another point, and build a whole dance of movements. They can test it all in slow motion before letting it run at full production speed. It's the direct handshake between a person's idea and a machine's action.
Okay, so we have these incredibly precise machines. We have the body, but it doesn't have a mind. It can't think for itself. It needs instructions. And that brings us to our next layer, the invisible but all-powerful layer of software, the code that gives these machines their marching orders.
And so often, when you're talking about controlling hardware directly, you're talking about the C programming language. It's been around forever, and for good reason. It's powerful, and it's fast because it's so close to the machine itself. A C program is really just a collection of functions. Think of them like little recipes. Each function does one specific job, and you combine these little recipes to build up the complex software that runs everything from your microwave to a factory floor.
Now, for a program to do anything useful, it has to remember stuff, like what was the temperature reading a second ago, or how many times is this loop run? It stores that information in things called variables. The easiest way to think about a variable is just as a labeled box. You give the box a name, you tell the computer what kind of stuff you're going to put in it, like a whole number or a letter, and then you can put information in and take it out whenever you need.
And right here, this is where software gets its real power. It's the ability to make a decision. The if-else statement is the absolute foundation of this. It's just a simple question. Is some condition true? If yes, do this thing. If no, do that other thing instead. This simple fork in the road is the building block for every single complex decision a computer ever makes.
And this is how those simple decisions get combined into something that looks like intelligence. This table, called a truth table, shows the simple rule for AND. The result is only true if the first thing is true and the second thing is true. If either one is false, the whole thing is false. It seems basic, right? But by stringing together millions of these simple logical checks, a program can solve unbelievably complex problems.
Okay, this next layer,
This is where things get really wild. So far, all our machines have just been following a script, a program that a human wrote. But what happens when we build machines that can learn from experience? When they can find patterns in the world all on their own? This isn't just control anymore. This is the dawn of intelligence. And the core idea behind this revolution is the artificial neural network. You've probably heard of it. It's a system of digital neurons that's loosely, and I mean loosely, inspired by the way our own brains are wired. The key difference is you don't program it with a bunch of if-else rules. Instead, you show it tons and tons of data, like millions of pictures of cats, and it literally teaches itself to recognize the patterns.
So what does this learning actually look like? Well, you can boil it down to a simple three-step dance. First, the machine has to sense the world, maybe with a camera or a microphone. Second, its software, that neural network, chews on that data, hunting for the patterns it's been trained to spot. And finally, based on what it finds, it does something. It acts. Maybe that's recognizing your face to unlock your phone, or deciding what song you might want to hear next. Sense, process, act.
So, we've done it. We've built this whole stack, from sand and metal all the way up to these learning machines. We've created a smart world. Now the question is, how do we, as people, plug into it? That brings us to our fifth layer, the interface between us and them. And right now, there are two really big ideas about how to do this. On one side, you have augmented reality, or AR. This is where you're still looking at the real world, but digital information is layered on top of it. Think of a surgeon seeing a patient's vital signs floating in their field of view. Then you have virtual reality, or VR, which does the exact opposite. It blocks out the real world entirely and plunges you into a completely digital one. So here's the simplest way to remember it. AR enhances reality, VR replaces it.
And that brings us to our final layer. This one isn't made of silicon or software. It's made of questions. Really big questions. Because now that we've built all this, these incredibly powerful and increasingly intelligent systems, we have no choice but to stop and grapple with what it all means. For us, for our kids, for our society. And the warnings, well, they don't get much more stark than this. This comes from Stephen Hawking, one of the most brilliant scientific minds in history. His fear was that if we ever create a true, full artificial intelligence, one that could improve itself, it could rapidly surpass us and see humanity as an obstacle. It's a sobering thought.
But then, on the complete other side of the coin, you have the builders, the innovators, the optimists. Mark Zuckerberg's view represents this perspective perfectly, that AI isn't a threat, it's a tool that will help us cure diseases, make our world safer, and solve some of the biggest problems humanity has ever faced, problems we could never tackle on our own.
So this is where it all leads. As we keep stacking these layers, the physical, the mechanical, the logical, and now the intelligent, we have to realize we're not just building better gadgets, we are, step by step, building artificial beings. And in doing so, they're forcing us to look back at ourselves and ask a question that used to be just for science fiction, but is now very, very real. In a world with artificial minds, what's so special about ours? What does it even mean to be human anymore?